Okay, we are jumping straight into computational fashion today with the paper ReFashion, Reconfigurable Garments via Modular Design by Lin, Lukács, and Leek.
Right, and the core problem that ReFashion is trying to solve is basically clothing waste. It's all driven by how static our clothes are. You know, conventional garments are fixed. They don't change when our bodies change or when styles shift.
And altering them is hard, sometimes impossible.
Exactly. So their solution is this really clever, computationally driven modularity. They break down any garment pattern, a 2D pattern, into a minimal set of reusable, standardized fabric blocks.
The foundation, pleat, and dart blocks, right?
Yep. Those are the three. And the real heavy lifting is done by integer linear programming, ILP. It's an optimization method that figures out the absolute fewest blocks you need to create the shape.
And then physically, you connect these blocks with things like snaps or brads, no sewing involved.
Which is the key. It means you can take something like, say, a pair of trousers, completely take it apart and rebuild those exact same pieces into a totally different garment, like a dress. It's all about longevity and reuse.
And this is all managed through a tool they built called ReFashion Studio, which helps with the design, the simulation, and even gives you the assembly instructions.
It's the full pipeline.
Okay, so let's unpack that foundational problem a bit more. I mean, anyone who's ever bought clothes knows this pain. You find a pair of pants, they're almost perfect, but they need tailoring.
And that requires a special skill set, right? Not everyone can sew. And even if you can, once you cut those pants into shorts, that's it. They're shorts forever. There's no going back.
The irreversibility is just, well, it's the core of the waste problem.
It is. And ReFashion flips that on its head. It introduces these modular design principles, think like Legos or IKEA for your clothes, where resizing, restyling, and reuse are baked in from the very beginning.
So to make that actually work, the researchers came up with three very specific guiding principles.
Yes, and these three principles really define the whole system. The first one is versatility, G1. The idea is that the modules have to be generic enough to build, a structured jacket and a flowing skirt from the same kit of parts.
Okay, that makes sense.
Then there's reconfigurability, G2. This just means the connections have to be reversible so you can take them apart, but also secure. No sew is the key here.
And the third one, which feels super important for a project like this, is wearability, G3.
Oh, absolutely. This is the one that so many theoretical projects forget. The final garment has to be easy to make, easy to assemble, and actually comfortable and secure enough to wear all day. I mean, if your modular dress pops open when you sit down, the whole system has failed.
Right. So those three principles, versatility, reconfigurability, and wearability, they're the foundation for all the computational rules that come next.
Precisely.
So before we get deep into the computation, let's talk about the physical building blocks. Everything is based on this standard unit, delta, which by default is 8 centimeters.
And that 8-centimeter grid is everything. It's the backbone. Every single module, every edge has to be an integer multiple of that delta unit. This strict grid is what makes the whole decomposition problem solvable for the computer.
So on that grid, the most basic piece is the foundation module.
Just a simple square block, a delta by delta, or some multiple of that. You could technically build a whole garment just from these, but it would be, very boxy. Fashion needs shape.
And that's where the other modules come in, like the pleat module.
Right. A pleat module is geometrically a square, but it has a special interface built in that tells the system how to create a directional fold. This is how you get things like knife pleats or box pleats to add volume and structure.
And then to make clothes actually fit a human body, you need darts.
Yes, and the darts are fascinating. They're designed to remove volume, to contour the fabric to curves, like at the bust or waist. The really key insight here is what they call the universal dart.
What makes it universal?
They constrain its width to be exactly equal to that base unit, delta. And what that does, and this is so clever, is it ensures that even after you've folded away the fabric to create the dart, the final assembled edge length is still an integer multiple of delta.
Ah, I see. So it stays compatible with the grid.
It stays perfectly compatible with all the square foundation blocks next to it. Without that rule, the moment you added a curve, the whole grid system would just fall apart geometrically. It's a really elegant constraint.
So you have the blocks, now you have to join them. The paper talks about point-to-point connections.
Right. Fasteners placed at these discrete intervals. And there are two main seam types. You have your standard flat seam, which is just a 1-to-1 matching of fasteners. Simple enough.
But then they have the gathered seam. It's a 2-to-1 ratio. How does that work?
Yeah, that's how you get soft folds and fullness. The system essentially takes the longer edge and bunches it up. It aligns every other fastener on that long edge with a single fastener on the shorter edge.
Okay, so it compresses the fabric.
Exactly. Think about the cuff of a sleeve or a gathered waistband. It's essential for making the clothes look less like, rigid geometric shapes and more like actual clothing.
And the actual physical fasteners they tested really highlight the trade-offs in the design.
Oh, for sure. They tried 3 types. First were these adhesive Velcro dots, super fast for prototyping, but they just don't last.
Not very durable.
Not at all. Then they tried standard metal snap buttons. They were really strong, which is great, but they create a lot of bulk. When you join 2 modules, you end up with 4 layers of snaps stacked up. It gets thick.
And the third option was brads, like paper fasteners.
Yeah, symmetric fasteners or brads. They were the best, aesthetically light, not very visible, and you can flip the modules over, but they were way slower to assemble, like 2 to 3 times slower than snaps. It's that classic engineering problem.
Right. You're trading sleekness and wearability for ease of assembly. Okay, let's get to the computational core, because this is where it gets really interesting for our audience. All these physical constraints we just talked about are why the ReFashion Studio tool has to be so strict.
That's the key takeaway. The computational constraints exist because of the physical limitations. You can't just draw any shape you want. You have to follow 2 main rules.
And what are they?
First, C1. All your pattern panels have to be perfectly aligned to that delta grid, no exceptions. And second, C2. You can only join edges if their lengths differ by, at most, a factor of 2.
Which guarantees that every seam is either a 1-to-1 flat seam or a 2-to-1 gathered seam.
Precisely. It keeps the physical assembly instructions simple and solvable. These rules define the input space for the optimization engine.
And even inside those rules, the editing process itself has a specific order.
Yeah, you can't just do things randomly. You have to apply shaping features in a set sequence. Gathers, then pleats, then darts. Because gathers and pleats are so disruptive to the geometry, you do them first. Darts are more localized, so they're calculated last.
I thought the way they handled those edits was really clever. The strip operations.
It's a great solution. You can think of the pattern like a big spreadsheet. If you need to add a pleat, you're not just moving a few cells around. The system inserts an entire row or column of delta-sized units.
So it's like adding a row in Excel. It pushes everything over, but keeps the grid intact.
Exactly. It guarantees the pattern stays orthogonal and delta-aligned, which avoids total geometric chaos.
But wait, if you do that, you must mess up all the seams on the edges, right?
You do, and the system handles that automatically. If a pleat, say, folds away part of an edge, the software instantly recalculates the seam connections. It redistributes those connection points to the neighboring segments to make sure the whole boundary still matches up perfectly. It's a really non-trivial geometric problem that it solves on the fly.
So once all the shaping is done, the gathers, pleats, darts, you're left with these complex polygonal areas that need to be filled in with the basic foundation blocks.
And this is where the integer linear program, the ILP, finally kicks in. And for the AI folks listening, the objective function is just beautiful. It is simply minimize the total number of foundation modules.
So it's basically a covering problem. You're trying to tile this weird shape with the fewest possible squares.
That is exactly what it is, a high-dimensional covering problem. The constraints are simple. Every little grid cell has to be covered exactly once.
But why choose to minimize the number of modules? Why not, the number of different sizes or something else?
That's the critical research decision they made, and it goes right back to G3, wearability and assembly.
Well,
Their hypothesis was that fewer parts equals a faster, easier assembly for the user. It's an optimization for minimizing human effort.
which means the solver will always prefer one big square over a bunch of tiny ones.
Always.
Oh.
And it works. The paper says these ILP problems solve in under a second, which is crucial if you want an interactive design tool.
So moving on to the results, how did this actually work in practice? Like for adjusting clothes to a changing body?
It worked incredibly well. For resizing, you just stretch the pattern on the grid, and the system instantly recalculates the new minimal set of modules you need. You only swap out a few pieces.
The maternity wear example in the paper was so compelling.
It really was. A user, P2, designed a top where you could swap in larger panels for the midsection as needed and then swap them back out later. You're not buying a whole new temporary garment. The fabric's lifespan is totally decoupled from the garment's current fit or style.
And the really mind-blowing examples are the extreme reconfigurations, taking the exact same set of physical modules from a pair of trousers and rebuilding them into a dress.
That's the ultimate proof of concept. And they even showed it works with recycled materials. They cut modules from old denim jeans, keeping the original pockets and seams, and integrated them. They even used hand-crocheted granny squares.
So the system is flexible enough to incorporate non-standard parts.
As long as they fit the grid. The user studies really backed up the value of this for non-experts.
Right. One user modified her maternity wear in under 5 minutes. Another one just started improvising, designed a top, then on the fly decided to make matching pants to create a jumpsuit.
It really supports that kind of spontaneous creativity.
The feedback that really stuck with me was the user who called it a Tinkercad aesthetic.
That's such a powerful comparison. It means the system is succeeding at making garment design feel accessible, like a fun digital tool. They loved the rapid prototyping and especially the sewing-free construction. It lowers the barrier to entry to almost zero.
Of course, it's not perfect. The researchers are very open about the limitations. The biggest one seems to be the sizing granularity.
For sure. All your adjustments happen in 8-centimeter increments. That's a pretty big jump. For a truly perfect, tailored fit, you'd probably need to combine this modular system with something more continuous, like drawstrings or laces.
And we kind of touched on this, but the ILP's objective function creates this inherent trade-off.
It's the efficiency versus aesthetics problem. The system wants to use big, efficient blocks. But if you want to design a cool, multicolored patchwork jacket, you actually want the most small pieces you can get. To do that, you have to fight against the optimization, essentially forcing it to make a suboptimal choice from its perspective.
And finally, back to wearability. Did the garments actually hold up?
It's a valid concern. One user worried about snaps popping open if they bent over. But the researchers did test this. They found that with the more durable fasteners, like the brads or denser snaps, the garments held up perfectly fine during day-long wear tests. So the choice of fastener material is absolutely critical.
So at the end of the day, ReFashion is this brilliant example of using computational optimization, in this case ILP, to solve a really complex physical problem. By setting up these smart geometric rules, they've made garment fabrication so much simpler and opened the door to a more sustainable, adaptable future for fashion.
It really is. And it leaves us with a fascinating question for the future of this field. The paper's ILP optimizes to minimize the number of parts, right? To make assembly easier. But is that the right goal? For the next generation of these systems, you have to wonder, should we be optimizing for minimal effort, which means fewer, larger modules? Or should we instead optimize for maximal aesthetic freedom, which would mean more, smaller, diverse modules? That choice, that core trade-off between assembly efficiency and creative expression, is really going to define what comes next.